So, in our last class we have seen Kirchhoff's law and their application, and we have seen how to solve circuit using Kirchhoff's law. So, we talk about Kirchhoff's first law, second law, and we have seen some circuit. So, today we will take some more circuits so that concept and its application part will get clear. So, let us start. Look at this one. So, arrangement is given and the capacitance is to be calculated. So, there are two spheres of radius A kept at distance d, which is very large as compared to the radius of a sphere, and we need to find out capacitance of this arrangement, right. So, first I will tell you the basic method. So, our basic method was we will give charge and then we will try to find out the potential difference, and charge by potential difference will give me capacitance. That was the procedure, right. For any new system we get, this is the procedure we need to follow. Now, so I will give plus q charge to this one and minus q charge to this one. As the separation between them is very large, the distribution of this charge over the surface here and over the surface here will remain uniform, right. So, this charge will get uniformly distributed as d is very large as compared to A. So, this will get uniformly distributed this way, and here you will get negatively charged particle on the surface which are uniformly distributed. So, this way charge will be uniformly distributed, and to get the potential difference, we know that the relation between potential difference and field. So, dV is equal to minus E dot dr we can use, right. So, using this I will get this, right. That means to get the potential difference we require electric field. So, if I take point which is at distance x somewhere here, as you can see the positive charge, this positive charge will produce field in this direction, and this negative charge will also produce field in the same direction. So, the net field produced in this expression I need to write net field produced. So, dV is equal to potential difference, dV is equal to minus integration net field. We need to add here, as charge is uniformly distributed, you can assume that whole charge is concentrated at center. From there at distance x outside, field is kq by x square. So, here I will write k q by x square plus this negative is also producing field. So, what is the distance of this point from the center of sphere? If total distance is d, out of that this is x, this remaining is d minus x. So, if I assume whole charge is concentrated at center, from center at distance d minus x, field produced by the charge, that is k q d minus x whole square, right. So, I got the value of electric field that I am writing in this formula to calculate the potential difference, and then dot dx. As I am going in this direction, field is also in this direction, dot product cos 0, field in this direction, I am going in this direction, further by dx. So, cos in dot product will become 1, right, cos 0 will be 1. So, if we can integrate this term, we will get the potential difference, right. Limit. So, when I am at x is equal to a, look at this one, because this whole thing will be at same potential, but the expression what you are writing, that as this expression belongs for this region only, then I have to start limit from this point to this point, right, from this point to this point, because the expression we are writing for the electric field that belongs to the region in between these spheres. So, limit will be x, we are starting from this point, x is equal to a, x is equal to a, we are on positive sphere V plus, then as I increase x, I will reach to the surface when the distance from the center, because I assume this x to be the distance from the center of this sphere. So, from center of this sphere to the surface of this sphere, this distance is d minus a. So, here I can write d minus a. Now, we need to integrate, and the limit this side will be corresponding limit this side. When you are on this surface, here potential will be say V minus. So, integration of this one will give you V upper limit minus lower limit V minus minus V plus, and get this minus this side, it will become V plus minus V minus, right, is equal to. So, I have taken this minus sign this side and converted the function into V plus minus V minus. Now comes first term. Okay, I will take kq out because that is common. So, kq out, and then integration of 1 upon x square minus 1 upon x. So, here it will be minus 1 upon x, right, this first term. Then next one will be, look at this term only, integration of d 1 upon d minus x whole square. Separately if I write, so integration of this so 1 minus will come due to power and another minus will come because of this x. So, this will become 1 upon d minus x, right. So, 1 upon d minus x I need to substitute here. Let us substitute. So, d minus x we need to write. With limit. Limit is a to d minus a and a to d minus a. I hope up to this everything is clear. So, when you substitute limit, then you will get v plus minus v minus as kq. Minus sign I can directly write lower limit minus upper limit a minus 1 upon d minus a, right, plus here this is plus upper limit minus lower limit. So, d, when I substitute d minus a in place of x, it will be like this, and then minus sign, and I will write d minus a. Now, you can see that these two are getting cancelled out, and here what we are going to get, that is in place of x we have written d minus x here. I can simplify it further, right. So, these two terms got cancelled out, and here we have upper limit minus lower limit, right, and here upper limit minus lower limit. So, in place of x, this is d minus x and this one is d, and then minus lower limit, right. And now you have potential difference. That I can substitute over here. this potential difference I can substitute here and simplify the whole expression, right. So, when I substitute the potential difference we are getting there after simplification, we will get C is equal to 2 pi epsilon naught A d minus A in bracket divided by d minus 2A, right. Look at this one. Now here the condition is d is very large as compared to A. So, if I substitute d very large as compared to A, this d is very large as compared to A, I can neglect A in comparison to d, and the whole thing, this d and this d will get cancelled out and you are going to get capacitance this way, right. As you can see, this d and this d will get cancelled out, you are getting 2 pi epsilon naught A, 2 pi epsilon naught A. So, this is one way of doing. We can do one more thing. If you look at the system, then we have got two spheres. Okay, I will keep this one as it is and I will erase the remaining part. So, this we were getting 2 pi epsilon naught A after using this limit. Now, what I am saying, directly you can get this result. If you look closely to the system, here we know that for isolated sphere of radius A, the capacitance is 4 pi epsilon naught A, Here this is one isolated capacitor, this is another isolated capacitor whose second plate I can assume to be at infinity, because in this case the second plate we assume to be at infinity, right. We got this capacitance. If we take a sphere of radius A, conducting a sphere of radius A, and we calculate capacitance, we will get this, we have seen in the last class. Now, what I am saying here, its second is at infinity and its second at infinity, its second one is at infinity, its second one is at infinity. So, that infinity they are connected, right. So, I can visualize this system as, see, so I can visualize this system as the infinity where second plate of this capacitor or second spherical shell of this one is placed and this one is placed, as they are connected, they are at the same potential. I can draw two plates which are connected and they are representing infinity, and this is one of the capacitor and this is another capacitor. So, their 1 plates are connected and other are open. So, you can see we are getting two capacitor in series. So, its second one is at infinity, its second one is at infinity, they are at the same potential. I can have two, here I am having two capacitors whose 1 plates are connected directly. So, we are getting this combination in series combination. This isolated one will have capacitance 4 pi epsilon naught A and this isolated one will have capacitance 4 pi epsilon naught A, and when you connect these two in series, formula is C1 C2 upon C1 plus C2. That means its capacitance will become half of this, both are same, series combination, it will become half. So, it will become 2 pi epsilon naught A. Look at this one. So, we are getting the same result whether we are following a complete procedure or we can take the help of already derived result. So, here I am taking the help of already derived result. We have one capacitor here, another capacitor here. I can see this as series combination, and the capacitance can be calculated from the formula C1 C2 upon C1 plus C2. So, with one step I will get the answer, right. Similarly, if I say, let us see another example, then it will be more clear. If I say two capacitors are connected by conducting wire, okay, here there are two capacitors which are connected by conducting wire. So, this say radius A and this radius A, initially assume both are of same radius. Now, their infinities will be connected, their infinity, as we can assume they are connected because they will be at the same potential, right. So, at infinity if I draw these two, they will have the same potential, right. This infinity one I am drawing for both the capacitor. For this capacitor, this plate, for this capacitor, this plate I am drawing here. Now, this one, look at this one here, this and this, these two are connected, right. So, it is parallel combination. What is the capacitance of this part? That is 4 pi epsilon naught A, and capacitance of this one, if I treat this as isolated one, that is 4 pi epsilon naught A, and if I ask what is the equivalent capacitance, then parallel combination formula is C1 plus C2. Directly I can add these two and I will get 8 pi epsilon naught A. If another one is having some different radius, so I hope this concept is clear. If I take this as something else like B, right, then so if I take this one as B, then the capacitance of this isolated one will be 4 pi epsilon naught A, while the capacitance of this one will be 4 pi epsilon naught B, and as these two are connected in parallel, I can write 4 pi epsilon naught A plus 4 pi epsilon naught B. In that case, the capacitance of this system will be 4 pi epsilon naught A plus B. Right. So, directly we got the value. So, previous case they were in series combination because they are in second plate which was at infinity, they were connected, but these two are not directly connected. So, series combination, and we got 2 pi epsilon naught A. Second case, these two are connected by a conducting wire, and then I am asking capacitance. So, these infinity ones, they are connected and spheres are directly connected. So, this space behaving as capacitor, this space behaving as capacitor, they are both the plates are connected together, right, this way. So, this is called parallel combination. I can directly write result. So, for all such type of problem, you can directly visualize the whole thing as a capacitor, and accordingly you can directly write instead of following the whole procedure, giving charge and getting potential difference. That will be a little lengthy. So, this will be easier one. Now, let us see another one. If you remember, is capacitance we got, if this one is A and this one is B, then we got capacitance as 4 pi epsilon naught AB divided by B minus A, right. While for that situation we got C is equal to 4 pi epsilon naught B square divided by B minus A, right, and we derived this result in our previous classes, right. Now, by today's logic, like what we are doing here, in the same way I can directly predict what would be the capacitance for this situation? When you earth the outer one, we know that whole charge appears on the inner one. So, minus q, this will carry minus q, this will carry plus q, this will be positively charged, and inner surface of outer one will be negatively charged. So, this will be negatively charged, right. So, the direction of field in this situation will be from positive to negative like this, right. So, as you can see in this situation, the space between two spheres behaving as capacitor, and we are getting this formula 4 pi epsilon naught AB divided by B minus A. While in this situation, if you remember, this was A, this was B, and earth gave the negative charge to this one, that was Q, times B by A, and then same amount of the positive charge appear here, and as it was isolated, outer surface will have negative charge like this. So, something like this we got there, and if I draw field pattern from positive to negative, lines will be like this inside, and outside it will be radially outward, right. So, you can see here that this space as well as this space, both the spaces are behaving as capacitor with inner one connected to 0 potential, and the one which we are assuming at infinity, that also will be at 0 potential. At infinity its potential is 0, right. So, if there are two capacitors which I can see, first one and second one, this is having 0 potential, this is having 0 potential, I can consider this as two capacitors where this one and this one, as they are at same potential, I can connect them this way, and as this surface you can see, this is common for outer one as well as inner one, that will have the single potential obviously, because this is a single surface, right. So, I can, for this part I can draw this plate, and for this part I can draw this plate, and I can connect them together. Now, let us see whether we are getting this result or not. So, the one we have here, which is representing this space, will have capacitance 4 pi epsilon naught AB divided by B minus A, right, and the outer surface, which in the previous case was not contributing to capacitance, start contributing to capacitance and behaving as isolated capacitor, because the second plate is at infinity. So, I can write its capacitance as 4 pi epsilon naught B. I am using the formula for isolated spherical conductor, right. So, now as I can see, both are connected in parallel formula is C1 plus C2. So, when I add these two, if I add these two, then you can see that C is equal to, I will write it here, so equivalent capacitance of this arrangement, C is equal to C1 plus C2, because both are in parallel combination. If you substitute value of C1, that is 4 pi epsilon naught AB divided by B minus A, right, and then second one I am getting 4 pi epsilon naught B plus 4 pi epsilon naught B, right. Now, if you simplify, as you can see, here we have B minus A, when you multiply it here, this will become B square, and another term you are going to get is minus AB. That minus AB will get cancelled out by plus AB, and after simplification we can see that 4 pi epsilon naught B square divided by B minus A is coming, right. This is what we derived there. Here we are directly telling this result by simple logic कि which two capacitors will be in series combination or parallel combination. So, I hope all these are clear. In first case they were in series combination, we got this formula. Whether you apply series combination result or finding electric field and then getting potential, we are getting the same result. Second case what we discuss, if these two are connected by conducting wire, then I can see this arrangement as two capacitors connected in parallel combination and the formula is C1 plus C2. I will apply C1 plus C2, I am getting 4 pi epsilon naught A plus B. Now, we took the problem we earlier discussed. So, there we solve it by the complete procedure, charge divided by potential difference will give you capacitance. But here by logic we are telling as this space is behaving capacitor, this 4 pi epsilon naught B minus A. While if inner one is earth, then outer is surface, as it will be having charge, that will also behave as capacitor. So, this is one capacitor, this is another capacitor, I can see these two are connected in parallel, I can directly write C1 plus C2 and get the result. So, I hope this whole concept is clear. Let us move to next one. So, sometime what happens ki a ladder will be given to you and you will be asked to find out the capacitance, equivalent capacitance, right. So, as you can see the units here are being repeated. These are the basic unit of the structure which is going up to infinity and these are being repeated. It depends on you how you want to see the circuit, because you can also see the circuit this way. You can also see the circuit this way. These are the units and they are connected, and in the last after all the units connected we have additional capacitor C. So, you may consider it this way or you may consider it this way, right. Any way you consider it, you are going to get same answer, right. What is the logic? So, as you can see that so many units are being connected in a very big building. If you just place one brick over there, the whole structure or the whole building will remain same, right. So, by just adding one brick in a big building does not make any difference. So, same logic we can use here, that up to here if I assume the capacitance of this arrangement up to here is something C dash or C equivalent or C dash, right. So, by just adding one more unit into the circuit, just adding one more unit into the circuit does not make any difference in the capacitance. So, capacitance will remain almost C. This is the logic we will use. So, let us see how to write it. So, up to here let us call it C and let us call it D. So, what I am saying is C equivalent between CD is assumed C dash, and if I just add one more unit in CD, if I just add one more unit, this is our unit, right. So, this unit keep repeating. So if I just add one more unit to this, then C equivalent across AD will remain same, right. So up to here, if this is C dash, I can again draw the circuit this way. This is our basic unit, this unit is here, and from here onwards capacitance is C dash. So C dash. So now I can see this C dash and this 2C, they are in parallel combination, and then after parallel combination this capacitor will come in series combination with this capacitor, and the capacitance across AB is C dash only. So I can write equation this way, you can see these two are connected in parallel. So the equivalent capacitance will become 2C plus C dash, right, as these two are connected in parallel. Now this and this, they are connected in series. Series formula is C1 C2 upon C1 plus C2, right. So what I can write, capacitance across AB as these two are connected in parallel, I can write C into 2C plus CD C1 C2 upon C1 plus C2, right. So this is nothing but a parallel combination, and what is CAB? This is B dot D, right. CAB across these two capacitance will remain C dash. So this is C dash only. So here I will write C dash. As you can see, we are getting a quadratic equation over here. When you multiply this term here, you will get a quadratic equation. Let's see. So this will become C dash C plus 2C C dash plus C dash square is equal to, this side we are getting 2C square plus C dash. So C dash here and C dash there, they get cancelled out, and the equation finally we are getting, I am writing it over here, there is no space, you can see C dash square plus 2C dash, get this term this side, 2C square is equal to 0, right. As you can see, quadratic equation, you can find out the root of this equation. So I can write the root of this equation minus b plus minus under root b square minus 4ac divided by 2a will give me the root of this equation. As capacitance cannot be negative, I will leave the negative root, I will take only positive root, and after solving I will get this one. You can simplify the equation and you can check, right. So this way we solve all ladder type of problem where basic unit kept repeating. So as basic unit kept repeating and you have already taken a very large branch, in that large branch you just add one unit, it does not change the capacitance of the system. So using that logic I am solving the equation, finally I got the quadratic equation for C dash or C equivalent. We are getting C dash, which is nothing but C equivalent AB. So the capacitance across these two terminal is under root 3 minus 1 whole bracket into C, right. This is the capacitance of the arrangement. Now if, let us see another concept, I will erase all the ink. If I say V volt battery is connected here, how much is the charge on this capacitor, or how much is the charge on this capacitor, or how much is the charge on this capacitor. If I ask what is the charge on the capacitor, or I may ask what is the potential difference across this capacitor, right. Here V volt battery is connected. So if I ask what is the potential difference here, CD, what is VCD, right? So you already have capacitance. If this is the capacitance of the whole arrangement, then I can redraw circuit this way, that V volt battery is connected and here we have got single capacitor whose capacitance is C in bracket root 3 minus 1. So if this is the situation, how much charge battery will deliver? Q is equal to CV. So Q is equal to CV, right? Capacitance here C equivalent. So the charge delivered by battery will be into V root 3 minus 1. So let us get back to the original circuit. It says that this much amount of charge will be delivered by V volt battery to the arrangement. So if I look at the system, battery will deliver this Q charge that will appear this way, right, and then this Q charge will get divided into two parts. Say Q dash follows this path and remaining Q minus Q dash follows this path. I got charge this capacitor carries, right. So once I have charge, this capacitance carries, here there will be distribution and one part will go this side, another part will go this side. Applying Kirchhoff voltage law, I can find out the potential difference. If you apply Kirchhoff voltage law here, you will get the potential difference across CD. Let us see. So this charge, I will write it separately, this charge what we are getting is CV root 3 minus 1, CV in bracket root 3 minus 1. Now I will use this result to find VCD. So this first part is over, second part. If I start from this point and again get back to the same point, then I can see minus V as there is increment, and then I am going from positive plate to negative plate, there is a decrement, that Q divided by C plus whatever the potential difference here, let us write VCD is equal to 0, and we need to find out VCD. Now value of Q I can substitute here. If I substitute value of Q here, CV in bracket root 3 minus 1, CC will get cancelled out, V here I can see V root 3 minus 1 minus V plus VCD is equal to 0, right, and this will become V and minus V, this will be V root 3 minus 2, V root 3 minus 2. On other side, when I send this term, I can rearrange it as 2 minus root 3 V in bracket 2 minus root 3. So VCD will be 2 minus root 3, and if you have the potential difference and you divide by the capacitance, Q is equal to CV, right, Q is equal to CV, then if you multiply this quantity to 2C, then you will get charge on this capacitor also. So step by step we start moving in forward direction and we can find the charge on every capacitor or potential difference across any branch. So first step was getting capacitance of the arrangement. Using the concept I told you, you will get the capacitance. Once you have the capacitance, first get the charge it carries, the charge it delivers or battery delivers. After you get the charge battery delivers, you can distribute the charge and you start moving in forward direction to find out charge on any of the capacitor, right. I hope this ladder problem is clear. Sometime what happens, instead of same unit repeating itself, unit will be changing. For example, look at this one, C, 2C, then this is 2C, 4C, and this one will become 4C and this will become 8C. See, something like this is given. So, here you can see that units are not being repeated. Every next unit is becoming double of the previous one. So, this is 2C, 4C and here it become 4C, 8C. So, next unit is not same as the previous one. This is the unit, but the problem is next unit is double of that, and then the next unit is double of the previous one. So, as you move forward, units are becoming double. It is not the same situation we have discussed here, where units were same, everywhere same. So, what to do in such type of cases when units are becoming double 4 times or any times like k times, then what to do? Now, if I assume that capacitance here is C dash, previous case we gave logic because all the units were same and adding a same unit, the capacitance is not going to change. Here unit is becoming double. So, if you go this way, then capacitance is becoming half, and if you go this way, capacitance is becoming double. So, if I assume this as C dash, then the capacitance for this part will be 2C dash, and capacitance if I take for this from here onwards, that will become 4C dash, twice of the previous one. So, this will be 4C dash. So, previous case it was C dash, whether you take unit or not, C dash, but here we have C dash double and C dash, 2C dash and 4C dash, right. Same way I can solve this problem also. What I will do, I will assume this whole thing as 2C dash. This capacitor is C and this capacitor is 2C, and the capacitance across these two terminals I assume C dash. So, first I will add all. As you can see, these two are connected in parallel, then this is first parallel, right. So, further I can reduce the circuit and circuit will be something like this. See, parallel combination I can directly write 2 times C plus C dash, right, and across these two terminals I want to find out capacitance. Now, these two are connected in parallel, I can write C into 2 C plus C dash divided by C plus 2 C plus C dash, right. These two are connected in series. Series formula is C1 C2 upon C1 plus C2, that I have applied, and the resultant what I am getting here, that must be equal to C dash across AB. So, this I will write C dash. Okay. Again you can see that we are getting quadratic equation. You can solve that quadratic equation now. So, C dash, and here this will be plus C dash to C plus C dash. On other side I am getting 2 C square plus 2 C dash, right. So, C dash here, C dash here and 2 C dash here. So this side I am getting 3 cc dash and here I am getting 2 cc dash. I can see the quadratic equation in c dash. So solving that quadratic equation, minus b plus minus under root b square minus 4ac divided by 2a, you will get the root of this quadratic equation and that will give you the value of equivalent capacitance across these two terminals. So there is a small change in the previous problem and this problem, or a small difference in the previous problem and this problem. This problem units are not repeating themselves, they are a particular multiple. In this case this is 2 times, it might be 4 times, 3 times or whatever be that, right. So it is 2 times. So as it is 2 times, if here it is c dash, if you move forward then it will be 2 c dash, if you further move forward then it will be 4 c dash, right. So using this logic I can solve this equation and by that I can find out equivalent capacitance of the arrangement. So I hope such type of problems you have got clarity. Now, so we have seen how to find out the capacitance when a totally different arrangement is given, two spheres connected or kept at some separation, concentric spherical shells, right, and such type of circuit where we have ladder concept and we apply Kirchhoff's law here. So let us take up some other circuit which involves switches, right. So switches are used to make or break the connection. So if a capacitor is connected to a circuit and we suddenly open the switch or close the switch, it might be possible that the whole equilibrium get disturbed. If whole equilibrium is getting disturbed, circuit will try to achieve new equilibrium. So in the process battery may deliver charge or may accept charge. I already told you all this. So now we will see some switch type of problem. So this is a circuit, as you can see that initially switch is open, this is switch which is used to make or break the contact, right. So initially this contact is open and charge will flow, steady state will be achieved, right. So in a steady state I can easily find out charges. As you can see that here capacitance will be 2C. So I am not applying Kirchhoff's law, I told you voltage division formula, by that I will solve the circuit. If you feel like applying Kirchhoff voltage law, you can check whether you are getting same distribution of charge or not, right. So I will try to solve it by simple method. So as I can see that we have 2C here and C here, directly I can tell about the charge if I have idea about the voltage division. So voltage division, when two capacitors are connected in series, the voltage will be divided inversely proportional to the capacitance. So the voltage coming across this, if I want to find out, then voltage coming across 2C is inversely proportional to the capacitance. What does that mean? This E is getting divided inversely proportional to the capacitance, that means C divided by C plus 2C. We have seen this formula in voltage division class, right. Similarly, if I ask what is the voltage drop across that capacitor, so that will be E into 2C divided by C plus 2C, right. So if you simplify, you can see that here we are getting E by 3 and here we are getting 2E by 3. Okay, so I straight away have voltage division, right. So this I can use to get the charges on capacitor. So here it is E by 3 and here it is 2E by 3. Now I will remove all this, right. I hope you understood voltage division formula. So I will erase this part. Now if this one is having voltage drop 2 E by 3, the charge on this capacitor Q, charge on this capacitor, that will be Q is equal to CV. That means 2 CE by 3 will be the charge on this capacitor. Without applying Kirchhoff voltage law, we got, and the potential difference across these two is E by 3, and this is nothing but two capacitors connected in parallel. So when two capacitors are connected in parallel, the potential drop across this will be same as this one, and that will be equal to E by 3. So the voltage drop coming here is E by 3 and voltage drop coming here is E by 3. So I can write here charge 2 CE by 3 and charge over here 2 CE by 3, right. Now we have a complete distribution, and what question says, the EMF of cell is E and the circuit is already in steady state if switch is closed, right. If switch is closed, find charge given by cell after switch is closed. So this is the complete question, right. So find the charge given by cell after switch is closed. So now system has achieved its equilibrium, right. So lower part of the circuit is not required. Now I will remove it because I used it for analysis. I will clear it. So this is the final distribution we had before closing the switch. Now what happens when we close the switch? As you close the switch, there is no use of this capacitor, right. Immediately its charge will become 0 because it is short circuited, its two ends are connected. So what I am saying is, when you have a capacitor which initially connected to battery, right, it carries some charge. This plate will be having plus Q charge and this will be having minus Q charge. If capacitance of this is C and potential is V, then this charge will be Q is equal to CV, right, plus CV this one and minus CV that one, right. And we have energy stored in the region this way in the form of electric field, and we calculated energy density for such type of situation. Now if I disconnect it from the battery after charging it completely and I will remove the battery. So I remove the battery, the charge will stay on the capacitor, once you fully charge the capacitor, and there is no further flow after it become completely charged, and then you remove the battery, charge will stay on the capacitor. So situation will remain this way. Now what I am saying, if you connect this plate to this plate by some conducting wire. So I have one switch over here and I am going to close the switch. As soon as I close the switch, immediately what will happen, because there is a potential difference between these two plates, this charge will rush towards this charge, and finally this Q, which is plus CV, that will merge with this minus CV, and total charge on the capacitor will become 0. So, finally what will happen, this charge gets completely, or this capacitor gets completely discharged. What happens to the energy which was stored here? That will go in the form of heat. At the joint there will be spark, and energy may go in the form of this spark, or energy may go in the form of radiation from here. All this we will talk later, right? When we will be talking about accelerating charge particle, at that time we will talk, right. So, right now we are just saying this whole energy will get completely converted into heat. So, energy wise whole energy gets completely converted into heat, and what happens, charge immediately rushes towards another plate and make the charge on whole capacitor 0. So, as you can I hope this whole concept is clear. So, charge capacitor, you want to discharge, just connect two terminals, touch each other, immediately within no time it will get completely discharged, right. Whole energy will come in the form of spark and heat, and you have to be little careful while doing it, because depending on the charge, the magnitude of a spark developed here will be different. So, a small amount of the charge, a small spark you will get, but if charge is very large, then you may get a large spark, right. So, while discharging capacitor you have to be little careful, but this is the procedure of discharging capacitor, right. So, this concept is clear, and I am going to use that concept in the circuit. Now, I am going to close the switch. As soon as I close the switch, this capacitor, it is connected by conducting wire. Now, there is no use of this capacitor in the circuit, right. These two capacitors will be there in the circuit. So, as there is no role of this capacitor now, circuit capacitance got changed to 2C, this one is C and this one is C. Earlier the capacitance of the system was 2C by 3. If you see that this is 2C and C, the C equivalent capacitance earlier was 2C by 3, parallel combination 2C and then series C, 2C by 3, and now the capacitance has become C equivalent because there is no use of this capacitor, it is short circuited. Short circuited means connected by conducting wire. So, two terminals connected by or two junctions connected by conducting wire, that is called short circuiting, right. So, as this is short circuited, there is no role of this one. Now, only these two are there. So, capacitance I can write 2C. So, you can see that capacitance here was something less as compared to now what we are getting. So, now we are getting 2C capacitance, which is more. So, earlier battery gave the charge according to this capacitance, now battery has to readjust the charge according to this capacitance. So, in the process battery may take charge from the circuit or it may deliver charge from the circuit. Procedure for that is same, right. So, finally what will be the charge? I can directly say that whole voltage will appear here and whole voltage will appear here. So, the final charge I am directly writing, final charge in the circuit will be, there is no potential difference here, this whole will appear across this and across this. So, here the charge will be CE and the charge on this one finally will be Ce, right. Earlier it was having, this was having 2 Ce by 3 and this was having 2 Ce by 3, right. Now from 2 Ce by 3 it has become Ce, that means what extra came, extra, I am talking about extra, what extra came is Ce by 3, it already has had 2 Ce by 3 and now finally its charge is Ce by 3, that means extra came is Ce by 3 for this capacitor. Same thing happens to this one, right. So extra charge coming into this capacitor is Ce by 3. If extra flowing through this one Ce by 3, extra flowing through this one Ce by 3, that means the charge coming into this arrangement from here, that will be 2 Ce by 3. That means charge given by battery is 2 Ce by 3. That is the extra charge after reconnection, right. So after you close the switch, equilibrium got disturbed. To maintain new equilibrium, battery give additional charge 2 Ce by 3 and that charge will flow this way, right. Whatever battery delivers, it receives, okay. And along with this process, there was one more process that is happening simultaneously, discharging of this capacitor. So this capacitor had 2 Ce by 3, this capacitor had 2 Ce by 3, that must also become 0 because it is short circuited. So if this is 2 Ce by 3, here it is 2 Ce by 3 and this charge must become 0. So charge from positive plate will go like this and it will neutralize the charge on negative plate and final charge will become 0. So as soon as you close the switch, this charge also immediately rush into negative plate. So charge coming from this side is 2 Ce by 3 because this must get discharged. As this become discharged, I will remove the charges appearing over the capacitor. Now look at the complete picture. 2 Ce by 3 and 2 Ce by 3 will make it 4 Ce by 3. So if I ask how much charge is flowing through switch, once switch is closed, how much charge is flowing through switch, that is 4 Ce by 3. If I ask how much charge, extra charge flowing through battery once switch is closed, that is 2 Ce by 3, right. So I can also ask how much is the heat generated in the process, right. So we know the formula, work done by cell after reconnection, we know the formula, work done by cell, change in potential energy or change in the energy stored in the capacitor plus heat generated. So you know initial charge distribution, you can find out the initial energy applying formula half q square by c. You have charges and you have capacitance. Similarly, you have final charges and you know capacitance, half q square by c you can apply. So by that you will get the change in potential energy. How much work that battery is doing after switch is closed, this across potential difference E, it is giving charge 2 Ce by 3. So work done by cell, if I ask, that is E into 2 Ce by 3, and change in potential energy you can calculate by applying formula half q square by c initial and half q square by c final. So this is final minus initial, that you can substitute here, get this term on other side, you will get the heat, how much heat is generated after reconnection, sorry, after closing the switch, right. So I hope complete concept is clear. So the charge flowing, the amount of charge flowing through cell, right? Okay, so hope everything is clear. Now let's move to next problem. The final charge on each capacitor. See, here question is, we already have two charge capacitors which are connected this way, and another capacitor is connected between these two terminals. You are asked to find out the final charge on each capacitor. Find the final charge on each capacitor. So this is a charged capacitor, initially charged capacitor, this is initially charged capacitor. How much would be the charge? You can multiply Q is equal to CV. So this will be 360 microcoulomb, and this one will be, this positive plate will be 300 microcoulomb. Okay, and we have got this as uncharged capacitor, right? So once it is connected, charge start flowing in the circuit, and question is, what is the final charge on the capacitor, right? So to get final charge, see, the procedure is, I don't know the direction of flow of charge. So what I will do, I will assume some direction. I will assume that Q charge is given by this plate which was having 360 microcoulomb charge, it gave Q charge. So leftover charge will be 360 minus Q, and on this plate obviously it will be negative of this value. How? Let us see. So Q charge goes and then it reaches here. This is having minus 300, this lower plate is having minus 300 microcoulomb charge, and it gets Q charge. It gets Q charge, so I can write it gets Q charge and it had minus 300 microcoulomb charge, right? This way I can write. This I will assume positive, because this, if I assume positive, that this is greater than this one, this plate will be positive and another plate, this upper plate will be negative. This plate will be minus of Q minus 300. Whatever it gets, it will give, that will appear here in front of that, minus Q, this is plus Q. Similarly, whatever it is getting, that will come here, right? Now you can see it had minus 360 and it is getting Q. So Q plus minus 360, right? Q minus 360, I can take minus out and I can also write this as minus of 360 minus Q, right? Now it looks better as compared to this one. I will write it this way: facing surfaces are carrying equal and opposite charge. Now let us apply Kirchhoff's law to get the value of Q. So if I move in particular direction, say this way, I start from this point and I will write it this way, right? Or I can start from this direction and I can go this way. So till now I have taken all clockwise. Let us take this as anti-clockwise. So if I am taking this as anti-clockwise, this way I will do. So I will start from this point and I will again get back to the same point. So passing through this capacitor, decrement I can see, Q minus 300 by its capacitance, that is 2, again decrement, plus Q divided by its capacitance, that is 1.5, plus here I can see increment, negative to positive, here I can see increment, right. Increment is taken with negative sign, so minus that is 360 minus Q divided by its capacitance, that is 3. Now if I solve this equation, I will get the value of charge. So let us see. So this 1.5 I can write 3 by 2, okay, just for simplification. So this 1.5 I will write 3 by 2. Now here I can see 2q by 3 and here I can see plus q by 3. So if I add, this will become q and then I have q by 2 here. So q plus q by 2 I can see 3q by 2. So 3q by 2. So all q we have taken. Now this is 150 with minus sign and this is 120 with minus sign. 150 with minus sign and 120 with minus sign will make it 270. 150 and 120 will make it. So if I simplify this and this will get cancelled out, I can see this one and then Q is equal to 180 I can see, right. So that means when these two terminals are connected here, this will be carrying charge 180 and here look at this one 360. If you substitute value of charge 180, you will get the charge on this capacitor. Similarly 180 minus 300 will give you charge on this capacitor. This way we have charge on all the capacitor. So here all the capacitors were having some charge, we suddenly allow a capacitor to get connected across these two terminals and then we calculated what would be the final charge on the system, right. So I hope all such type of problem you can easily solve. So to get more problem and for practice, you can download the assignment from Yup Master app, right, and you can post your doubt over there. I will clarify that doubt. So I hope you enjoyed today's class. Thanks for watching.